span continuous beam of ABC is fixed at A and simply supported over the support at B and C. So you have a two span and one end is fixed and the rest of the two end is being hinged. The span is 6 meter and 6 meter both of them, and you have the moment at the one span between B and C. You have a moment which is clockwise moment of 40 kN/meter, and at A and B you have a uniformly distributed load. You have to find the bending moment. So this is the case by using matrix stiffness method. First you should find the kinematic indeterminacy, that is Ki. So I have given the formula for kinematic indeterminacy, and if you could recollect, the formula is Ki equal to number of joints. How many number of joints are there? A, B and C. There are three number of joints, and into degree of freedom. What is that? 3. So you have to multiply 3 into 3. So what will be your answer? It will be 9 minus support reaction. This is your formula. Ki equal to number of joints into degree of freedom minus support reaction. Now the support reaction is for the fixed end you have 3 number of reaction, and at the hinged end you have 2, and at another end you have 2 number of reactions. So totally 3 plus 2 is 5 and 7. So totally 9 minus 7 will be 2. So this is your kinematic indeterminacy. This kinematic indeterminacy is how much of movement is possible in a joint is known as kinematic and kinematics. I have explained in the last class. Kinematics is the movement of any joint. So kinematic indeterminacy is a joint it is not possible to move, and since it is fixed it will not move. So B joint will be having some movement. What will be the movement? It will be rotational movement. So this beam or this support can rotate. It is possible, and at C there is a possibility of rotation for this beam. Okay, these are the two indeterminacies. So where these kinematic indeterminacies are there? At the joint B and joint C. Okay. Now next step is finding the fixed end moment, that is fixed joint force. Since you know this formula, it is uniformly distributed load. If you are substituting WL square by 12, so this is your formula for A to B and B to A. It will be minus and plus. And for a moment, if you have a moment in a span, and if it is a clockwise moment, both the terms will be positive. MF B to C and MF C to B will be positive here. And what is the formula? M by 4. What is M? M is moment. 40 by 4 is your formula. If in case this is anti-clockwise moment, your formula will change into minus M by 4 and minus M by 4 at both the sides. This is the differentiation between load, that is a uniformly distributed load or point load, versus the load which is given in terms of a couple or moment. Okay. Now your answer would be minus 60 plus 60, both are plus 10. Okay. Now next step is finding the joint force. At A to B you got anti-clockwise moment of 60, and B to A you got clockwise moment of 60 kN/meter, and at B to C you got the value of positive. Both are positive. This is clockwise and 10, and C to B also is clockwise of 10 kN. So these are the joint forces. Now how to find equivalent joint load is, where are the kinematic indeterminacies? So these are at the joint B and C. Okay. Now what is the total moment acting at the joint B? Since this is positive, see MF B to A is positive and MF B to C is also positive. So both are positive. Okay. Let us find beta matrix. What is beta? Is known as transformation matrix. Now you have found out that joint B and joint C has the kinematic indeterminate joints. Now let us apply a unit force at the joint B. If you twist this joint, what happens? This beam will bend like this at A to B. Since you are twisting at the joint B, you will be having a bend like this. You have to apply a clockwise moment and you can see this kind of a pattern. And what will be your transformation matrix here? That is 0 at joint A, there is no rotation. At joint B to A will be 1 and B to C will be 1 and C you don't have any rotation, that is 0. Now apply a unit load at the joint C. So you apply a moment here and at C you will be having 1 unit, rest of the place at 1, 2, 3 and 4. So at the remaining places you will be having 0. So 0, 0, 0 and at last joint you will be having 1. So these are the two transformation matrix. Okay, now you can combine. Note that in matrix flexibility method you had B star and B naught. These are the two cases. But in terms of stiffness method, you don't have B star and B naught. Only beta matrix is there. There is no component on split up. So it is very much easier than matrix flexibility method. And what is P naught value is the forces at element coordinates in fixed state. Do you have any joint load? No. P naught is the force at element coordinates in fixed state. So what are they? Yes, these are the fixed force, minus 60, plus 60, 10 and 10. You can see these values. So these are the fixed end moments, that is fixed end moments. Okay. Now what is F naught? This is step number 3. F naught is beta transpose into P naught. So what is beta transpose? You can convert rows into columns. So you have 2 beta component and 1 row. You can multiply row into this column. What will be your answer? 0 into minus 60 will be 0. 60 and 1 into 10 will be 10. So you will be having 70 and another value will be 1 into 10 is 10. So you will be getting 70 and 10 as your answer. And force applied at system coordinates. F of F. Do you have any force which is acting at joints? At B joint you have no force. At C also at A. So there is no force which is acting at the system coordinate. Okay. Now the step 4 is element stiffness matrix. Okay, how to find the element stiffness? You have formula EI by L 4224. Now can you recollect the flexibility matrix? So there you have used the same kind of formula, that is flexibility matrix. Here you are using stiffness matrix and there you are using flexibility matrix. So what is the difference between that? There you used L by 6EI 2 minus 1 minus 1 2, isn't it? So here instead of that formula you will be having stiffness matrix formula, which is EI by L 4 2 and 2 4. So this is your formula. EI is taken as it is and L, what is the first span length? Which is 6 meter, and what you can do is you can divide for all the components 4 by 6, 2 by 6. If you are dividing, you will be getting 4 by 6 is 0.67 and 2 by 6 is 0.33. Like that you can find K2 between B and C. Now for the stiffness matrix B to C, the span you got the length of 6 meter. The same way you can divide for all the components, you will be getting EI. So K1 and K2 both are in terms of EI. You can take it outside and you will be getting the stiffness matrix K, element stiffness matrix, EI equal to the 2 component. So the rest of the diagonals will be 0 here. And what is system stiffness matrix? How to find that? Capital K. Find the difference for this step. Element stiffness matrix is small k and system stiffness matrix is capital K. And what is the formula? beta transpose small k into beta. What is small k? Just now you have found out element stiffness matrix. Okay, what is beta transpose? Which is the beta value you got here, element stiffness matrix into beta. So if you multiply these three components, you will be getting k as 1.33, 0.33, 0.33, 0.67. First you have to multiply beta transpose into k, and by that answer you have to multiply into beta. If you have done that, you will be getting the answer of this component. Now how to find the k inverse? Your inverse of the matrix is interchange the sign. You have to interchange 0.67 and 1.33, and this component will be minus. Now you have to do that, and you have to find determinant. So 1 by determinant. What is determinant? Multiply 1.33 into 0.67. So you will be getting 1.33 into 0.67 minus 0.33 into 0.33. So this is known as determinant. So determinant of component is you have to multiply these two. So you will be getting 0.77 as the answer, and you have to divide that determinant of A. So what is the formula? How to find inverse of any matrix? 1 by determinant of the A into the change of the sign. So now if you divide 1.33 divided by 0.77, so you will be getting 1.71 is your answer, and 0.33 divided by 0.77 you will be getting 0.429, and 0.667 divided by 0.77 you will be getting 0.857. So these are your values. Now you can interchange. So this is the way to find inverse of the matrix. Now next step is finding u. What is u? The system displacement are given by u equal to k inverse f of f minus f naught. What is k inverse? You know the k inverse value is here, and f of f is the component, the answer you got here. Yes, f of f is 0 and f naught is 70 and 10. So these are the two values what you got here, and you can use the same value. The k inverse, the value you got here, and f of f and f naught. So you have to multiply these two component. Since it is 0, you will be having minus 70 minus 10. You can multiply 0.857 into 70 and minus 0.429 into 10. You will be getting one answer, and second answer will be 0.429 into 70 and 1.717 into minus 10. The answer will be minus 55.71 and minus 12.86. So this is your system displacement matrix. So for each and every step you have a letter, and for a letter you have a indication. So that is the explanation, abbreviation. Okay. So now you can find the element displacement matrix. This is system displacement, and del is element displacement. How to find that? U is system displacement. What you got is minus 55.71 and minus 12.86. You have to multiply by beta. 0 into 0 will be 0. So first component will be 0, and second 1 into 55.71 will be this answer. The same way 1 into 55.71 and 1 into minus 12.86 will be this answer. Force P dash equal to K into delta. And what is K? You know the element stiffness matrix, and you have to multiply with this delta, and you will be getting this answer. What is K? See, this is the K matrix you got here, and you have to multiply this matrix into the del. So this is the del value here, So you will be getting a negative value. So this is minus of 12.86, and if you multiply these two component, you will get P dash, which will be 18.57, 37.14, 32 and minus 10. Okay, now you have to find the final force Pf equal to P naught. What is P naught? Fixed end moment, and P dash is the value what you got now. And you can just add this, you will be getting 78.57. This will be 22.86, 22.86, and last will be 0. So this is your solution. Now you can find the positive bending moment. Since it is a UDL, WL square by 8, you will be getting 90 kilonewton per meter, kilonewton meter, and for a moment your formula is M. So whatever the value you are getting, you can take that. So this is the moment between B and C. This is the moment at this junction, and the negative bending moment is 78.57, and at the junction B is 22, at C is 0. So you have 0 here, you can connect that, and the positive bending moment is this. At this point you will be getting 40, that is minus 20 and plus 20. So both will be in addition, you will be getting. So the formula will be M by 2. So by this way you can find the bending moment of this